used for mainly for the defense purposes. That means in order to identify what is the location of the position of the enemy and so on, and accordingly the strategies have been met out. So, and finally, US has taken a lead, and he launched his first satellite in 1959, the Explorer 6, which was mainly designed for observing the cloud cover over the Earth's surface. And in 1960s, they launched the next satellite, that was Tyros 1, and that was mainly concerned with the observation of the weather on their part. And see, in 1917 only, we got this Landsat 1, which was the first non-military satellite launched by the USA. And in between, particularly in 1960, the US also launched the Corona satellite series, which was a spice satellite for US, and that was solely meant for the defense purposes. And recently, only in the year 2017 and so, they have declassified those Corona images, and now people are still working on them. So this was the brief history about the you can say foreign satellites or US satellites, but India was not very far behind. India has launched their own independent satellite Aryabhatta in 1975. This was India's first satellite, and afterward India has grown up like anything. They have their own fleet of various kind of launch vehicles and satellite vehicles, right from the SLVs, ASLVs, PSLVs, GSLVs, and GSLV with the Mark III. So these are all, you must have seen this particular in a latest movie called Mission Mangal. So this was the geosynchronous launch vehicle, satellite launch vehicle, which has been used to take the Mangalyaan to the space. So this particular slide shows us the complete Indian satellite program, which has been started from 1975, and it's all on the way. So we have variety of satellite now. We have an INSAT series, which was mainly focused on the weather forecasting kind of thing. The IRS series, which have been mainly for the various resource mapping for the Indian landmass. And we have also gone into the radar imaging, and we have coming up IRNSS satellite, which was mainly for the satellite navigational things, and Gagan. So you can find more details in the website itself, the ISRO website itself. So now we come, what is remote sensing? What do you mean by remote sensing? So remote sensing is nothing but it is a process of collecting data or information about an object. It may be about a phenomena, but the condition is that the information has to be collected from a distance and without coming into direct contact of that particular object or phenomena. So the simplest example of the remote sensing is when you take a photograph of any person or place, then you take the photograph from your camera and you don't come directly into contact of that thing, but you capture most of the image, like what kind of color of clothes she is wearing, or on which object she is sitting, and what is the background information in the photograph. So all kind of information we get from that photograph. So the simplest example of remote sensing is the photograph. So more commonly in this course, we are talking about remote sensing, not from the camera. It is mainly from the satellite data, or you can say satellite sensors. So these sensors actually on board on a satellite platform with a variety of bands, or you can say variety of resolution information, and finally we get information on of the object of the Earth. Like it may be information on the agriculture, it may be information on the water, information on the forestry, and so on. So if you come to the definition, it is a practice of driving the information about Earth's land and water surfaces using images acquired on an overhead prospecting using electromagnetic radiations in one or more region, and so on. So I will come to the principle of the remote sensing, then we will cover this in detail. So this slide shows us what are the different types of remote sensing platform we can have. So first one can be an airborne platform, which can be onboard on a this aeroplane or helicopter. There may be they may be considered as a aerial photography, or other sensor also can be boarded on the airplane. And there can be satellite platforms, like obviously these must be a satellite which are far away from the Earth's surface. And there may be some ground-based sensors also, which can be mounted on a high crane. And then actually the ground-based platforms, they mainly used for designing the satellite sensors, which has to be sent in the space. So this slide actually is very important, which tells us why we need remote sensing, or what are the main advantages of the remote sensing, why we should go for remote sensing instead of a manual monitoring, or you can say terrestrial monitoring. So first and foremost, that remote sensing offers a very cost effective observation or monitoring, you can say. It covers a very large area and it's having a synoptic view. It's very much time efficient as well as accurate. That means, yes, every satellites have a revisit time, or you can say we have a regular time interval. We can have the data for a particular area. And there are a lot of satellite data which are freely available, so we need not to spend a single penny from our pocket in order to get those data. So as well as there is a fast extraction of the data from any kind of GIS software. It may be ARC, or it may be QGIS, and so on. We will come to that also. As well as the sensors can turn out to be many wavelengths in a spectral electromagnetic spectrum. So the variety of information we can capture when we have a multi-band sensors on board in the satellite. Apart from that, first and foremost, that we can also have the data inventory from the inaccessible areas, like high mountains or the glacier areas where we cannot go very easily. But the remote sensing data we can always acquire those areas. So these are few of the key advantages. Yes, this particular slide indicates the major components as well as the basic principles of the remote sensing. I have written over here, if you see number A is nothing but it's a source of energy. In most of the remote sensing products, sun acts as a source of energy on the earth. And here you can say B is a process which actually involves the radiation and its interaction with the atmosphere. So V is over here. So whatever radiation we are receiving, it must be passing through the atmosphere, where it is interacting with the atmosphere. And C is the interaction or the target point on the Earth's surface, wherein the radiation is imparted, and a few part of the radiation maybe get absorbed by that object or the surface, and few of that maybe get reflected, and those reflected radiation actually received by that recording sensors which are on board on the satellite. So once the radiation or the electromagnetic information is being recorded by those sensors which are present at D, and then those information can be transmitted and it can be received at a ground receiving centers, that is GRC. In most of the countries, they have their own ground receiving centers. In India, we have this GRC near to Hyderabad, and place is called Sadhnagar, which comes under the NRSC, which is the leading agency, leading space agency in India, which controls all kind of satellite data reception in India. And once we got data transmitted or received at the ground receiving center, and that data can further be interpolated, it can be refined, the information can be enhanced, and finally those information can be used for various kind of applications. So the G part is the application part. So this is the whole, you can say, cycle of any remote sensing processes, right from the source to data generation, to data interpretation, to the application. So these are the major component and principles involved in any kind of remote sensing. So as I told you, this electromagnetic radiation, the EMR, is very, very important in any kind of remote sensing. All of us know that the electromagnetic spectrum is a very wide thing, which is mainly constituted about electric field as well as magnetic field, which are actually moving perpendicular to each other and moving forward, right? And they actually travels with the speed of the light, right? So if you see, this is the complete spectrum of that EMR. So the smaller or narrower bit here you can see right from the 400 to 700 this thing nanometer wavelength, which is a visible spectrum, and apart from that, that means this particular portion of the electromagnetic radiations which our eyes are sensitive to, which that means our eyes only can see into this particular spectrum. But see, you can see there is a large range of the wavelength which is available in both sides of this visible range. So there is an increase in wavelength, and frequency is just inversely proportional to the wavelength. So there must be a decrease in the frequency as we increase the wavelength. So but the satellite sensors are designed in such a way so that they can see or they can visualize the things in different spectrum, like infrared regions, or you can say the microwave regions, or in the long wave radio regions, and so on. So how this Earth's surface is interact with the EMR is given in this particular picture. If you see, so there are few phenomena happen when the radiations from the sun passes through the atmosphere and received to the ground. So there are some transmission through the atmosphere, right? So there are different kind of dust particles or aerosols or clouds are present in the atmosphere. They actually causes some kind of scattering phenomena also there. Some absorption also happens in those particles, and remaining whatever the remaining radiations which receives to the ground, it again gets some kind of scattering, and few of that radiation get also absorbed in the Earth surface itself. Mainly the infrared or the NRI or near infrared radiations which absorb in the daytime, and the Earth also emit those radiations in the night time, and few of the radiation also get reflected, and that reflected radiation again I have told you that being captured by the sensors. So some kind of emission also happen in the night time. So these are the various phenomena which are the mainly happens when the EMR interacts with the Earth's atmosphere as well as surface. So yes, here you can see the basic principle of remote sensing, which is nothing but the reflection from the object. So you might learn this into your schools, that why this green leaves appear green to us. It is because of that, because it absorbs all other kind of radiations and it reflects only the green radiation, so it appears green to our eyes. So this is the basic of that remote sensing. So some of the incidence radiation get reflected, observed, and transmitted. So green vegetables or green leaves appears green to us, right? So we will come to that also. Reflectance is an important, the most important, you can say, phenomena or processes in remote sensing. So the Earth's different kind of features, they are characterized by the different percentage of the EMR, which is reflected differently in different wavelength zones. So it may be getting a little bit confusing, but I will clear this thing. So the reflectance of different objects in different wavelengths are varying for different objects. So this is a basic for remote sensing. And there is one more term called spectral signature, which are often represented as the plot or the graphs with against the wavelength in a horizontal and the percentage of reflectance in the vertical axis. So the spectral signature of particular object, it looks like something this. So if you see here, there are wavelengths which are in nanometers. So here you can see these are the blue color wavelengths, green, red. This is near infrared, and this is the mid infrared. And if you see this sand color graph of water, so here you can clearly, we can identify that into near infrared wavelength, the reflectance of water is almost zero. That means whenever we will see water bodies into near infrared bands, the water body must be appearing like black or dark blue, you can see. So we can easily identify the water presence in the near reflectance, NIR. Similarly, in the near infrared bands, you see the reflectance of this particular green grass is very much. It is around 40%, even 50%. So you can easily identify the difference between the water and the vegetable, particularly in the near infrared. Similarly, different objects. See, in the same near infrared, you see the red band. If you see red band, the dry grass and the green grass having a different, very much different reflectance. So you can easily identify or distinguish between these two objects. So these are just few examples, and similarly different objects, like it may be buildings, it may be a riverbed, it may be a barren land. So different objects having a different reflectance into a same or this thing wavelength, a particular wavelength. So in that way, those can be distinguished. So now this slides shows us or indicates about what are the different kind of remote sensing sensors. So those sensors are broadly categorized in two categories. First one is the passive sensor, second one is the active sensor. So passive sensors are actually those sensors which measures the energy which is naturally available. That means it is some kind of reflectance from the sun. That means sun is providing some radiation, it is being reflected, and those reflected radiation is being captured by the sensors. So those sensors are called the passive sensors. So most of the sensors are passive sensors. And active sensor, as the name suggests, these sensors actually having their own source of energy. That means they actually first emit the radiations to the Earth's surface, and whatever the reflected radiation from the Earth are being captured by the sensors. So these are active sensors. So the radiation reflected from the target is detected by those sensors, right? So what is the advantage over active sensors? Active sensors, see, in the night we don't have this sun, so the active sensors can be operated in the night as well as. And people have done some more modification in the active sensors, and they have provided the radiations which can penetrate through the cloud covers. As you see, if some clouds are there, so that the sun cannot penetrate those clouds, so again we don't get the appropriate information. But once you have the active sensors, and you may design the radiation in such a way so that they can penetrate the cloud, so that the requisite information can be get from those sensors. This slide is about the satellite orbit. So you see the satellites, there are different types of satellite, mainly two types of satellites. I will come to that also. So but every satellite, each and every satellites have a fixed rotational orbit, you can say. And the height of those orbits are very much purpose driven, or very much you can say scientific in nature. See, yeah, the figure will clarify you more. So there are two types of satellite. One is the geostationary orbit satellites, and second one is called the polar orbit satellites. So the geostationary, as the name suggests, geo, that means the earth, stationary matlab the stationary. That means this particular satellites, actually the earth is revolving in this way, right? And the satellite is also revolving with the same pace as the earth. So what happens? This particular satellite looks stationary to Earth at particular point. So this is called geostationary satellites. So these geostationary satellites actually focus on a particular part of the Earth and keep on focusing on this particular area or region of interest, right? So what kind of information we can get from here? So what is the advantage? We will see that also. But there is one more satellite called polar orbit satellite. As you know that Earth is revolving like this. But our polar orbit satellites, they actually revolve perpendicular to the rotation of the Earth. So what will happen? So this type of satellite, the solar orbit satellites, they will cover the entire Earth in one complete rotation of the Earth, right? So yeah, here you can see the differences or advantages of these two different kind of satellites. So geostationary satellites, they provide a big picture, so enabling us the coverage of various weather related information or events we can get. That means most of the meteorological or weather forecasting satellite like IRS series or INSAT series, they are mainly the geostationary satellite, which are being used for like local storms or what kind of some kind of tsunami or cyclones are coming or not, right? And polar orbit satellites, these are actually called the Earth resource mapping satellites also. So what is happening? They are operating as a sun synchronous orbit. And what information we are getting? We are getting what are the different kind of terrestrial changes which are happening over the Earth's surface, and not only in particular part, but in a complete globe. Those kind of information we can get from this polar rotating satellite. Yes, the resolution is an important aspect in remote sensing. If you see, there are four types of main resolutions in the remote sensing use: the spectral resolution, radiometric resolution, spatial resolution, and temporal resolution. So we will see them one by one. So spectral resolution is mainly concerned about how many bands you are using in a particular satellite or this thing. So you see, it reflects the band of the width of the spectral bands. Like that means it simply represents how many bands are present in a particular satellite product. If it is a monochromatic sensor, that means there is only one sensor at particular wavelength is available. If there are multispectral sensors or multi-band images are available, that means it may be at the order of right from more than one, that means from 2 to 15 channels, or it can be hyperspectral, that means hundreds of bands are available on that satellite on board, and which can the variety of information can be achieved. That means we can get information from different wavelengths, right? Blue, green, red, as well as infrared. So and this two more bands are there. So complete see 5 number of bands, 6 number of bands are there. So number of bands is represented by the spectral resolution. The radiometric resolutions, it actually is represented by the number of the digital level which is used to express the sensor outputs. So in simple terms, actually it defines how many bit data you are getting, right? It may be 1 bit data, it may be 4 bit data, 8 bit data, or 16 bit data. So what do you mean by that? If it is a 1 bit data, that means it's 2 to the power 1, that is two variety or two values are present in one band. It may be 0, it may be 1. If it is a 4 bit data, then 2 to the power, that is 16 type of values, 16 values, right? 0 to 15. That means 0, 1, 2, 3, 4, 5, and up to 15. These values are presented in a one band, right? If it is a 8-bit data, then one band or one pixel having a 2 to the power 8 values. It can accommodate the value between 0 to 255. That means obviously higher the bandwidth or higher the radiometric resolutions, the variety of information you can capture. But obviously it also costs in the data volume. So we need to be, you can say, it's a trade-off kind of thing. That means at what radiometric resolution we need to settle down, right? Like the Indian remote sensing satellites, they quantize with a 256 level, that is equal to the 8-bit radiometric resolutions. So if you ask somebody about the radiometric resolutions, then he is going to answer it's 8-bit data, it is a 4-bit data, it is a 16-bit data, and so on. And the data, higher the bit, higher the number, higher the gray shades you will get in your imaging. And spatial resolution, if you talk about the application of agriculture and you can say hydrological application of remote sensing data, the most important resolution to us is by spectral resolution, which actually represents the, you can say, it is the distance which in between you can identify the two objects or two data points. Obviously, higher the spectral resolutions or finer the resolutions, better is the information you capture. So here you can see an example. This is the spectral resolution is 1 kilometer of NOAA, and the width and let's see it's around 36 meter. So you get this kind of information. And if you have a cartosat image with you, which is having a 2.5 meter spatial resolution, you can get more details. So the finer the spatial resolution, better the information and detail the information. But again it will cost you more data volume when you go finer things. It is very logical. It's similar to, you can say, scale of a map in survey of India's topo sheet, wherein you can get the map of 1:250,000, which is having a coarser information at India level, and you can also have a map of 1:10,000, which may be getting information on a district level or taluka level. So it is similar to that. Temporal resolution, as I told you that each satellite actually revisit to that particular location at particular time interval, and that time interval actually is called the time resolutions, right? It can be referred as a frequency at which the images of a given geographic region can be acquired by the satellite. So this temporal resolution is also important in agriculture and hydrological studies, as we want to see that suppose we have sown a crop and we want to monitor that crop growth in different seasons, right? Right from the sowing season to the maturing season to the harvest season. And we just want to identify what kind of changes we are taking. So, for example, if you see date 1, this was the scene. Some places they don't have agriculture, or you can say vegetation, and after some time again you have again at certain interval of time you monitor the things with the remote sensing data, and you find that there are significant change occur between the first and the last images. So while analyzing those images, you can easily see what kind of changes you are getting. Yeah. There are one more term in the remote sensing which is frequently used, called the false color composite. So before that, we need to understand that the individual bands, when they capture the information of a you can say object or the region, all they present in a gray scales, right? And these gray values actually depends, it may be from 0 to 255 if it is a 8-bit data, so which is the case. So there are different bands, band 1, band 2, band 3. So different bands actually highlights different kind of object. Like band 3, it is actually highlighting the water bodies. So herein you can see this is a canal, clear command. A canal is there. This is river Ganga. It is a imagery of Haridwar region, and this is a small river which is actually crossing that, passing that canal, also coming here. And once you actually display, while seeing this gray pictures, you cannot visualize the things very clearly. In order to visualize those gray pictures or gray images, so displaying those in a color composite images, mainly into three primary colors, which are sensitive to our eyes, is red, green, and blue. We need to use this false color composite, right? And once we combine those gray images or different images, different bands or different band combinations, then we get something like this, where we can easily identify. So this cyan color area is mainly the settlement area, and this, the dark black color, you can see this is the water body, and this reddish color, you can see this is vegetation. So there are different kinds of features which can be identified while we can have different band combinations. So you can find those in any remote sensing book. So I will just show you this picture. It will make you more clear on that. So once you have a FCC or false color composite combination with the different bands, so you can identify different kind of features with approximately color. It basically, this is the information we are getting from the satellite which are far away from us. So we need to go for a ground truthing of those classification, or those, you can say, clustering. Like for example, the deep water is normally presented by the dark blue or black things in the FCC. A shallow water can be represented by a light blue things. Vegetation, always a healthy vegetation, which is always a bright in nature, red bright, and dark red, you can say, and some agriculture vegetation which are not at the maturing stage, which they may appear light red, like barren area, which actually represented in the moderate to reddish white areas, built up area, mainly in the bluish gray places, like here, right? Salt affected area, and clouds and snows, they actually appears in the white color, right? And this is a traditional combination of the FCC when we are using the Landsat images. But this combination may be changed in the different, you can say, sensors or different satellite data. But mainly concern is that the NIR band should go into the red channel, the red band should go to the green channel, and green band should go to the blue channel. Then only this kind of FCC can be created. All the remote sensing images, they are actually made of small pixels. If you keep on zooming the remote sensing images, then finally you will get these pixels values, or pixels, which are nothing but a square block, and which is having a particular value, and it may be varying from 0 to 255 in case of 8-bit data, and that particular value is called the digital number of that pixel, right? So if you consider a remote sensing image, it is nothing but it is a combination of those pixels. So it can be considered as a matrix of the individual points or the pixels. And pixel is nothing but it is a picture element. That means the smallest part of a picture is a pixel, right? And each of the pixel is being defined with particular values called the digital value or digital number. And based on the properties or reflectance values of different objects, like herein you can see this is completely water, so it must having a very low digital number, like it may be near to 0, or it may be ranging from 0 to 5. And this white portion, it must be having a higher value, it may be close to say 255 or 240, 260, something like this. So based on reflectance values of those objects, we can identify the objects. And those objectives are nothing but the cluster of various pixels. So similar is the case of the, there is nothing, the similar kind of information we can, I have already told you, this is a picture element, pixel, and this particular value is a digital count, or you can say digital number, DN value. And obviously these values ranges from 0 to 55 in case of 8-bit data. And all the images are combination of rows and columns, right? And similar kind of things you can get in the multispectral data. So don't get confused. Multispectral is nothing but it's a multi-band data. So here in the picture you can see this is band 1, band 2 and band 3. 3 bands are here. But for the same pixel, you can say in the particular image, you may have different reflectance. Like the same object present here, which is having a reflectance value of 35. In case of band 1, in case of band 2, the reflectance value is 42. In case of band 3, the reflectance value of 125. So the object is same, but in different wavelengths, the reflectance values are different, right? So here you should understand this is the concept of multispectral images. So what we are doing, we are actually capturing variety of information while we are using multi-band images. There are some corrections also or enhancement also we need to do while we are using those images. It may be geometric correction, atmospheric correction. So see, lot of errors may be there in the remote sensing data. So we need to rectify those errors before using those data. So these are few of the corrections and enhancements which we can always apply to satellite data. It may be due to presence of the various, molecules, aerosols. There may be some errors in the sun angles, age. There may be noise in the data, or there may be some onboard disturbance in the satellite itself. And there are many techniques are available to correct those things as well as enhance those images. And yes, I believe these are the most commonly used vegetation indices which are commonly used for agriculture management. So these are mainly vegetative indices. If you see the difference vegetation indices, ratio vegetation indices, this is very popular. Normalized difference vegetation index, this is called NDVI, sorry for this. This is NDVI. And as well as SABI is also an important vegetation indices. So variety of indices people have given, and they uses a different bands. So if you see, these bands are a combination of, you can say, matrix. So just like any other matrix, we can always do matrix to matrix multiplication, addition, subtraction, or any kind of mathematical operation we can perform on the those bands pixel to pixel. So if you have a near infrared band and red band, so you can always get this kind of information. So with the combination of various mathematical expressions, we can enhance our desirable vegetations. So NDVI and SABI, these are most importantly or most commonly used indices. One more important aspect in agriculture point of view is the image classification or satellite image classification, which is used as spectral informations to distinguish or to identify the different kind of objects. Like if you want to see what is our agriculture area, or if you go to the second level or third level land use land cover classification, then you can also identify what are the different kind of crops are available in different agriculture fields. So we need to actually train obviously it has to be done with the software, and mainly the ADAS software is being used for classification, and QGIS is also having capabilities for classification. So they actually use the, if the variety of or cluster of pixels having a similar kind of reflectance values. So those cluster can be classified in one class of a land use. Like there, obviously, if there is agriculture field is completely wet, or paddy field is there which is filled with the water, and there is one more field, wheat field, which is not having significant water. So the reflectance of both the fields is naturally getting more. So we can easily, the satellite images, from satellite images we can easily identify the different kind of fields. And once we identify those fields, we can convert those into, you can say, shapefile in order to get the area of our desired classes. Yeah, there may be different type of remote sensing, so I don't think this is very much, but it's very easy. If you talk about in terms of spatial resolutions, there will be low resolution system, medium resolution, high resolution, as well as very high resolutions. So it all depends on the spatial resolutions, right? And if you talk about in which spectral region the data has been acquired, so it can be classified into optical imaging, or it can be thermal imaging, it can be a SAR imaging, that is a synthetic aperture radar, which is mainly active sensing. So again, optical and thermal, they can be defined based on the number of bands. It can be monospectral or monochromatic or panchromatic, multispectral, superspectral, or the hyperspectral. So hyperspectral system may having hundreds of the bands. So it is all the terminology. If you see, if you just read on that, you can simply understand what do you mean by that. And the SAR imaging system also can be classified according to the combination of various frequency bands. There are different bands, and there may be single frequency band like presence of C band, X band, a K band, L band. There may be combination of these 2 or 3 bands. There may be a single polarization like VB and HB and VB, and there may be a multiple polarization. So these are all not that these are all technical terms, but we are, if you see at a application part, so we actually go for multispectral, single frequency are also sufficient for agriculture applications. But if you want to do some advanced analysis, then you can always go for that. Yes, the data volume is an important aspect in this remote sensing techniques. As I have told you, this is just for example. See, there is a 3-band multispectral images of 8 band, and if you are having a 20-meter resolutions, and if you want to cover the 60 by 60 square kilometer of area, so then we must have this 3000 by 3000 pixels per images. But if the same area has to be covered with a higher resolution, say 10-meter resolutions, and we have only panchromatic or single this thing image, but the resolution we have just make a finer. So the total pixels will be around 6000 by 6000 pixels per images. So again, it will be a total of 27 million bytes per images. But herein, you see just one band, but the spatial resolution is very less, so it is around 36 million bytes per images. So in that way, if you see the spatial resolutions, if you make it fine, then your data is going to be much higher or much more bulky. So thus the panchromatic systems are normally designed to give a higher spatial resolution than the multispectral systems. So we need to trade off. That means what kind of data we need, what kind of information we are looking for, or at what scale we are doing our analysis. So we come to the data sources. The satellite data sources, there are abundantly available data satellite sources are available in the web. So if you see for Indian scenarios, the Bhuvan is the best platform in order to get the spatial data. So there are variety of data is available at Bhuvan platform. So I'm not going into details. I will share this PPT with you so that you can share the follow these links in order to get the data. So there are a lot of free hydrological data is available for India. It is from the India virus, which is being maintained by the CWC. And if you talk about the global data set, so This is a wonderful site. That is from USGS USA Earth Explorer, which actually provides all kind of remote sensing data and DM data sets. It also includes the IRS, the Indian remote sensing satellite data, also being included in this particular portal. So you must explore this. Apart from that, for agriculture point of view, we also need some kind of socio-economical data. So all world level socio-economic data is also available from this CDEC site. In free time, you can also explore this. And there are few also high resolution data is also available from this Alaska satellite facility, particularly the digital elevation model, which is available at 12-meter resolution. And yes, this is very interesting tool which is called the land viewer. It is very interesting in that sense that all the previous website I have told you, those actually provides you data, but this particular land viewer provides you the data as well as you can do some preliminary processing on the data for your study area alone. So you must explore this particular site. Now a brief intro about the GIS. So it starts with the geographical. So geography plays an important role in our life. Like we need to find out what is our nearest, you can say railway station or petrol station, or what should be the optimum rule for laying a water supply pipeline, or what should be a layout for a rural electrification or electrification of power lines. Or if you talk about the defense, then we need to understand what is our strategic positions and how we are going to defend that. All this kind of information or application, they need geographical information. So in that sense, geography plays an important role in our life. And the word GIS is made of geographical information system. So geography mainly deals with the science of Earth's features. That means what is there and where it is. And the information is nothing. It is about the data, attributes, or the information of any object. And system is nothing, but it is a set of things which operates in synchronized in order to perform a defined task. So in most of the cases, our laptop or system works as a system. So by definition, it is a database management which captures, stores, manipulate, analyze, retrieve, and display. So this GIS has to perform all this kind of tasks, and this has to be done spatially as well as non-spatial data both, right? So GIS is an important framework because it understands the processes, it understands the patterns of the various physiological processes of the earth, and finally it also helps in modeling the things and visualizing the results. So it is a technology which integrates the following: the remote sensing, the mapping, the GPS, the computer, RDBMS, or you can say survey, field data, and modeling, and so on. The countless. So in simple things, GIS is actually looking at the different layers of a region at a time. That means we can deal with all kind of data like elevation, transportation, or addresses, boundary, water features, survey, or whatever your data, all soil, geography, users name, agriculture, land use, all kind of layers can be, all kind of operations can be performed in a single go in all the layers. So this is the beauty of the GIS. So this is also a very beautiful slide I've taken from one of my friends. So it actually defines what is the difference between the data and the information. Data can be anything, like this is the data. But how we derive the information from the data, once we restructure the data in a meaningful manner, then we come to a information. And this information, this is actually a descriptive information, and it can be a graphical form also. And once the information is linked with the graphics, then it becomes the geographical information. In GIS, we have mainly two types of the data, which is also important to understand: the spatial data, obviously data which are related with the space or a particular region or particular location, those are called as spatial data. For example, the road map, the city locations, the land use. Like the capital of the India is Delhi. The location of Delhi is not going to change. So the location of Delhi is a spatial data, right? The non-spatial data, it mainly deals with the attribute or characteristics which are related with the spatial, even with the non-related with the spatial as well as, for example, all the you can say all the information like rainfall, temperature, RH, the snow, these are independent of the locations. Like if Delhi is having rainfall of say 80 mm and Agra may having a rainfall of 70 mm, or Agra may not receiving rainfall at all. So the rainfall or temperature, these are independent of the locations. These are the spatially varying things. So these are non-spatial data. So there is a question for the audience. Do you agree that mass is a non-spatial data and weight is a spatial data? Do you agree with this or not? Just tell me in the comment box, okay? And these are the various components of the GIS. It mainly includes the hardware, software, dataware, humanware, methods. Obviously, humans are very much required in order to operate all the things. And these are the steps involved in any kind of GIS-based analysis. It all starts with the data collections, which may be a field-based data, it may be cell-type data or something. And then data storage must be there, which actually related with the database management. Then data manipulation, some kind of you can say image processing, rectification, or image enhancing. These are the part of the data manipulations. And then we do the data analysis, which actually involves the modeling, different kind of analysis in that. And finally, once we get all kind of analysis, we need to display or disseminate that data in forms of the images, graphs, maps, and tables, and so on. So all these 5 steps are a must for any kind of GIS-based analysis. Why it is so special? I think I can skip the slides. Basically, it provides a very fast processing, and we can do multiple tasks at a time. And most importantly, it's very much cost effective. That means a lot of automation can be done in the GIS, and it can answer most of the questions like what is this, where it is, what is the change, what will happen if we do this and that. So all kind of analysis we can do into GIS. So again, this is the similar kind of thing, the potential. And yes, there are variety of GIS. You simply name the things like there are desktop GIS, there are mobile GIS, web GIS. There are recently people are attempted on virtual reality GIS, and the most easy example of web GIS, which all of us are using knowingly or unknowingly, is the Google Earth. Whenever, or Google Map, you can say, whenever we want to travel somewhere, we just type our destination location, and the Google Map, it provides us the route, optimum route with a lot of information. That is the best or easiest example of the web GIS. Yeah, there are a lot of softwares are available for GIS. So these are the proprietary or the commercial softwares, and these are the open source softwares. So we used to prefer to work on the ArcGIS for the commercial versions, and in case of free GIS, I usually work on this Quantum GIS, which is very much high potential software, and it is very much easy to use as well, and a lot of technical support is available online. And once you do or start applying these GIS, you can use those in GIS in variety of things, like you can create your own agriculture information system or water information system or land information system. People have attempted on biodiversity information system, forest information system. So you just take the particular stream and put the information system behind that, and you will get a solution, right? And there are a few basic terms in the GIS which are very must. Scale, obviously everybody knows the scale, but it is a ratio of the distance on the map which has equivalent distance in the ground. So 1:250,000 in Survey of India topo sheets. Obviously I have already told you. So Coordinate system is a reference system which is representative of locations of geographic features. See, our map projection is also very much important. See, our Earth is a geoid. It is not a proper sphere. You can say it's a sphere, but it is not a perfect sphere. So once that is a 3D object, and when you are converting that 3D object on a plain paper that is in 2D, so certainly there are some deformations happens. In order to tackle or handle those deformations, these coordinate system and projection has to be selected very wisely for every particular reasons. The coordinate system and the projections have been given. Now, usually people are doing this UTM, WGS84 and UTM projection systems. Resolution is also one of the important aspects, which is nothing but it is the smallest feature which can be recognized on an image. Again, it is related with the pixel size of the image. So, if you talk about the data models in GIS, so there are mainly two types of data model. One is called the vector data model. Second one is the raster data model. So, anything in a real world can be represented either in the form of point, either in the form of line or polygon. So if you talk about the points, so point can be a representation of well, or it can be a re-engage, it can be a village, a town, if you talk about a bigger map. And the lines the roads, the railway networks, the canals, the boundary, these can be represented by a canal or the line features, right? And the polygons are nothing but simply it's a cluster or it's a closed line on the basins, boundaries, the forest areas, agricultural lands, or the cadastral maps or ponds, lakes. These can be actually represented by polygons. And if you're working on village level, then your complete village boundary itself can be a polygon. If you right. So what is the difference? So these are actually discrete object views. If you keep on zooming, it is not going to be deformed. So you will always get some line, polygon, or point in your map. Similarly, I have told you there is a raster data model, which actually nothing but it's a representation of pixels which are arranged in a matrix. So again, all these three objects like the point, the line, and the polygon, these can also be represented by a raster data model. But again, one point will represent a one pixel, and if you take an array of pixels, a connected pixels can form a line, and if you see a cluster of the pixels, this will represent a polygon in case of the raster data model. So both the data models are very much useful, and their applications are equally important in different aspects. So geodatabase is nothing but it's a database management system only, but only thing is that actually it is representing or storing the geological information, so that is why it is geodatabase. So variety of information can be stored in geodatabases, like it can store annotations, dimensions, feature, classes, or you can say the location, topology, tables, and so on. The people from the computer background, they must be understanding what is the database and how the data is being stored in the RDBMS. Metadata is also an important aspect if you are considering remote sensing and GIS technique applications in your studies or in your analysis. So before using any kind of data, you need to see what is the quality of the data, and that quality of the data easily can be find out in the metadata information. So it is nothing but the information or data about the data which you are going to use. So it actually provides you the fitness of the data sets, what is the quality of the data, whether there are some cloud covers present in the center data or not, what was the data format is available, what was the data, you can say format, date of record, what is the sun angle, what are the softwares which are compatible with this data, what is the data volume, and what are the what kind of code is required to access those data. So all those information about that data can be found out in the metadata. So it is highly recommended that you have to go for metadata information first before using this data. So these are few of the applications wherein you can use the remote sensing and GIS combinedly. So you can see all kind of sectors I have written, like meteorology, hydrology, soil sciences, forestry, agriculture engineering, environmental study, and so on. So we will talk in this detail just in few slides. So if you talk about the natural resource management, so resource assessment, change reduction, suitability analysis, impact assessment, these kind of analysis can be done very easily with the help of RS and GIS. So these are the few things which can be done for the water source management particularly. If you see this Jal Shakti Abhiyan, which has been initiated by the Ministry of Jal Shakti in the last July 2019. So what they have done, they have started with a GIS layer only. So this is a block level map of India, and red spot, you can say these are the blocks which are severely water stressed and which has been targeted or identified for this Jal Shakti Abhiyan at the ministry level. So GIS is actually helping you to identify your target areas wherein you have to start your activities. And the blue map, you can see this is the flood map. Zoning has been done for a river. So it is a case of New York City. Yeah, if you talk about the agriculture, I believe, so the crop water requirement predictions, which is mainly deal with the irrigation water requirements, the crop acreage and the yield estimation of particular region or the basins or the command areas, the crop condition assessments, the soil moisture evaluations, and the suitability mappings. These all can be done with the help of GIS. And recently, there's a WA plus, that is water assessment plus framework has been developed, which actually assess the water productivity and the land productivity of a command area of or a basin. So all this are the potential use of GIS in case of agriculture. If you talk about disaster management and mitigation, so a lot of weather forecasting about the storms, tsunamis, or you can say the uh, yeah, dots or so many things. This can be predicted by the remote sensing satellites. Apart from that, during the disaster, also as well as post-disaster assessment, damage assessment can also done with the help of remote sensing. If we talk about the forestry management system is being used by the MOEF, and it is actually using for forest resource mapping, reporting the wildfire fights, assessment after the forest fires, and so on. Encroachment is an important aspect which actually the forest department is looking into. Obviously, defense services, they are using this remote sensing and GIS rigorously. Recently, you must heard about this Balakot strike, in which a lot of defense satellite has been contributed in order to identify the exact location of the enemy training camps or terrorist training camps in order to strike them. Emergency response services, they are also using this GIS services. You see 108 emergency services, they have their own complete GIS network with them. So once they receive a call, they identify what is the location of that call and what could be the optimum route of the nearest ambulance of 108 ambulance, and what could be the optimal path to that ambulance in order to reach to the calling position or calling locations. So they are using this GIS technique rigorously. Infrastructure planning can be easily done with the, suppose you are planning some kind of highway, so urban department or urban ministry, they are using this GIS in many things, highway planning or railway track survey and so on. Urban planning and management is also being used. They are also using this remote sensing and GIS technique in order to predict what will be the urban growth clusters in the next 20 years, 30 years, and 40 years. We have also done some kind of analysis, and we will share into the next session also. Business GIS, this is the latest development in GIS, wherein the business houses actually they are maintaining their business with the efficient supply chain management. They are locating strategically their stores near to the populations or near to their consumers, while doing some kind of demographic analysis, or you can say logistic availability. Presently, if you must have heard about this Swiggy, and this one more food app is there, so that you simply order on your app and they will find your way, food way. Uber is also using this GIS. So Uber, Swiggy, all these apps, they are actually using the web GIS in order to reach you. So there are not many applications of GIS being used. So as I told you, this slide is only about this quantum GIS and QGIS. This is maybe probably the second last slide of this session. So it is a free open source GIS, which is wonderful really. And because you can use this GIS because it's free, and it can be operated in Windows, Linux, as well as Mac. And you can also make your own codes if you're having a coding experience, and you need not to pay anything. See, just like in case of the history or ArcGIS. So QGIS, highly recommend you to you try to use this QGIS. Lot of tutorials also are available on the YouTube, so that you can use that. So it is just about QGIS. I'm skipping that. And a lot of help is also available online for the QGIS. So you can have your own understanding help with this community. So I have taken a little longer time. So thank you very much for this particular lecture. Thank you. So over to you, Saurabh. If any questions are there, please let me know. Saurabh? Saurabh?
Hello.
Saurabh, if there are any questions, so we can take that.
Okay, sir. If there are no questions, sir, we can take a short pause and
Yeah,
can start the next lecture series. That's the hydrological application of remote sensing and GIS in a short while.
yeah.
Yes, sir.
ഇത് വരുന്നുണ്ട്. അത് ചെയ്ത് കെട്ടിച്ച് അത് എവിടെ സ്റ്റോക്ക് ചാർജെന്നും പറഞ്ഞ് എഴുതുന്നുണ്ട്.
നോക്കട്ടെ, ഒന്ന് വിളിച്ചോട്ടെ.
Yeah, welcome back. Should I start now, Saurabh? Saurabh?
Hello?
Saurabh, should I
Yes, sir.
start?
Yes, sir, you can start this.
Okay. Can you see my screen now?
Yes, yes. Screen is visible.
Okay. Good afternoon to all. So, in continuation to our remote sensing and GIS introductions, now we are moving for hydrological applications of the remote sensing and GIS. So, hydrological applications mainly involve the dealing with the water resources, and why this water resource is important to us. So, this is the scene of India. So we are having around 18% of world's populations, and we are having only 4% of world's water resources. And apart from that, we are only having 2.4% of land resources. And apart from the human resources, we also cater to a population, great population of livestock, which accounts for around 15% of world's total livestock population. So in overall, if you see, we have to feed animals, we have to feed humans, we need to water for agriculture, we need water for industry, and the water resources are very much less. And this is also a report published by the World Resource Institute, wherein it has been said that 54% of the India faces high to extremely high water stress areas or regions. But I still believe that India having a lot of water, or India is still a water-rich country, only that we are lacking is the proper management of the water resources. So the remote sensing and GIS technique can also be used for managing our water resources in a more efficient manner. So these are an important tool in hydrology and management of water resources. If you see water, its occurrences varies spatially as well as temporally throughout the hydrological cycles. And if you talk about India, we have a very low rainfall areas in the western India, like Rajasthan is there, maybe 100 mm of rainfall, annual rainfall. And we have a very high rainfall regions also in the northeast, which are receiving more than 11,000 mm or so. So this shows the high variability, spatial variability of the rainfall, and which actually corresponds to the water resources in India. So in order to study that, the remote sensing and GIS are actually practically very applicable. Apart from that, water resource assessment and management, these are geographical activities which requires handling a lot of remote sensing spatial data. So again, the data as well as handling those data, we need some kind of GIS, geographical information system. So thus the various combination of GIS simulation models can be efficiently used for handling such remotely sensed data. This particular slides you have seen in the previous session also. So again, it representing the various kind of hydrological applications or water resource management applications. For example, the water resource assessment, flood mapping and management, hydrological modeling, land use change detection, modeling and planning, the drought monitoring, irrigation water management, evapotranspiration estimation, soil erosion, potential evaporation and modeling, snow melt runoff modeling. These all are the activities or the applications which can be achieved while using this remote sensing and GIS techniques. If we talk about the floods or the management of the floods, so what kind of things we can do? We can create the near real time flood indentation mapping. We can also do flood damage assessment. We can do the flood risk zone mappings and vulnerability assessment, or it can also provide inputs for the real-time flood forecasting and spatial warning systems. So here in the figure you can see this flood hazard zonation has been done for the Dhemji district in the upper Brahmaputra river valley. So you can identify the red areas which are representing the high hazardous zones. So a lot of attention has to be paid by the local administration during the flood period or the rainy seasons in order to avoid the casualties or the infrastructural damages. So variety of zones you can identify, or flood zones you can identify with the help of remote sensing and GIS labs. And as I have told you, you can always overlay a different kind of layers. It may be of mandal, taluka, districts layers, and then you can further go down and drill down the things and then get whether your area of interest or your area of interest of reason, whether it comes falls under which category, so that accordingly you can plan the things. This is another image which represents the flood monitoring, its extent, duration, and depth analysis. These are the picture from the Western Odisha, you can see. So here you can see these are the remote sensing images of different days. This is the 4th September and 19th September. So here you can see this is the black one is the spread of water. So you can easily identify on the 4th of September there are a lot of water or water-led areas were there, and the water has been receded completely in the 19th of September, by 19th of September. So in that manner you can identify what are the area which needs your direct attention or where the immediate action has, what kind of immediate actions you need to take. So it all related with the decision making at the executive levels. All this information can be used by the local administrations. As I told you, the flood damage assessment also can be done with the help of remote sensing. So here is the example of the flash flood which has been occurred in the near to Leh city in the Ladakh region. So it is no more JNK, it is Ladakh UT now. So the flood has been occurred on the 6th of August. So this is the cartographic image of July 16, 2010 prior to that event, and after the event on 12th of August, this is the cartographic image where you can easily identify these are the different mud flow, you can say signatures you can easily identify at different places, and what are the different kind of damages which has happened to the connecting road, or you can say the boundary wall to a particular premises. This is the military premises actually. The boundary wall what damaged after that flood. So all this kind of flood damage assessment can be done with the help of remote sensing and GIS. Flood inundation mapping and monitoring also can be done. So this is a study, a case study which is done by the Bora in 2018. So what they have done a flood inundation study in the Kaziranga National Park in the Assam. So Kaziranga National Park is a unique place for the biodiversity. It is mainly famous for the single horn rhino over there. So every year, a lot of animals they were washed away by the floods, and that's why they have to migrate on the higher grounds in order to save their lives. And with the help of the Sentinel-1 SAR images, they have identified the safe zones or the safe areas which are very much crucial for identifying the location for building the animal shelters, and as well as finding out the escape routes or the rescue routes for the local tourists as well as for the local people. So you can see over here different types of sentinel images as well as their classified images, which actually represents the spread areas as well as their extent, or with us two-dimensional analysis we can also find out the what is the depth of the water level in those areas, but again the ground truthing has to be done for those models. So these are the live examples wherein the remote sensing and GIS can play a life-saving role for various things. And if we talk about the hydrological modeling, I'm from National Institute of Hydrology, so I'm very much interested in this. So if we talk about a hydrological system, so or the watershed or a basin, so it is nothing but it's a place wherein one particular water cycle or hydrological cycles take place, wherein you can see water get evaporated from the oceans, it get condensed in the form of the cloud, and further the cloud moves up, and when they get cooled cold enough to get precipitated, and the precipitation that may occur in the form of rainfall or in the form of snowfall, and the precipitation, some part may get absorbed by the soil, some maybe get intercepted by the vegetation, few of them may go inside the soil as an infiltration, and few of part of it may go as a runoff or subsurface flow, which again appears to the ground. And finally, there's runoff joined to some streams, stream joins to river, and river finally again back to the oceans. And the infiltration also, some of the infiltration also goes as a groundwater recharge, and few of the groundwater also flows in terms of the base flow. So this is a complete water cycle wherein we have a major source of energy is the sun. So if you take example of hydrological model, so we have three components: the inputs, the system or the model, and the outputs. So there are a variety of inputs which can be included in a model or a system which can act on a system. There may be some climatic forcings which mainly includes the precipitation, maybe rainfall, maybe snowfall, the maximum minimum temperature, radiations, relative humidity, wind, and so on. It also includes the land use, land cover presence in the system, what kind of soil or what kind of soil texture is present in the system, what is the elevation profile of that system. These all are the input for any kind of hydrological model. And these hydrological model actually they uses some kind of mass or momentum balance equations, or they uses the energy balance equations in order to find out the desired or the requisite outputs. And the main outputs what we focus as agriculture or as a hydrologist, we are very much interested in the runoff, which actually deals what amount of water is available at the outlet, what is the ET. That means ET actually is important in order to identify, in order to calculate how much water we need to supply to our irrigation fields. Soil moisture is an important aspect or important output, which actually defines that when we need to irrigate our fields, if there is a particular level of soil moisture goes beyond that point, then the soil achieves to a permanent building point, then the crop dies. So that these all inputs or outputs are very much important for any kind of hydrological or agricultural planning, or what kind of sediment is coming. So this is all about the hydrological modeling. So if you see precisely, the land use is a spatial information, soil is a spatial information, and the elevation is a spatial information. And these spatial information, obviously we will get from the remote sensing satellite data easily, and we can do the analysis in the GIS software. So a simple example, this is a study what we have done for a basin in the central India. It's a part of Mahanadi basin. The basin is called Sivnath basin, which is in the very central part of the Chhattisgarh, wherein you can find Raipur somewhere there. Raipur, Durg, Vilai, and somewhere here in Bilaspur is there. So this is a DEM, digital elevation map of the waterside or the catchment, and this is the rainfall map, this is the land use, land cover map, and these are the location of various climatological parameters, mainly the rainfall and the temperature. All the data has been taken from the India Meteorological Department, IMD. And once we have given this all input into a hydrological model called SWAT, that is Soil and Water Assessment Tool, which is a very robust, semi-distributed hydrological model, then we have produced this discharge at the outlet of the basin, wherein we can always do some kind of calibration of the model. And once we are satisfied with the calibration result, then we go for the validation of the model. And once we done the calibration and validation of particular model, then that model can be used for short-term as well as long-term predictions of the discharge values for a given input, and mainly the future inputs may be mainly from the climatic data as well as from the the land use data. I've told you this prediction, or you can say the detection of the land use land cover change is an important aspect from agriculture prospects as well as from hydrological prospects. So again, the same basin we have considered, and here you can see these are the land use land cover maps of the same basin for different years. Like this is for year 2000, 2005, 2010 and 2015. So from the figures itself, you can easily identify that these are the urban clusters which were present in the year 2000, which are mainly the Raipur and Durg Bhilai, and these has been expanded very much in 2015. And for the new urban clusters, like here you can see this is the Bilaspur and this is your Rajnandgaon region, which has been expanded in the last 15 years, right? And these are few of the different classes of the land uses, and they got different kind of changes. Obviously, if some classes are gaining the, or it is increasing, so definitely it must be at the cost of some other classes. In this case, the reducing class is the agriculture, although there is not much reduction, but yeah, from 76.75% to 75% is the reduction in the agriculture, but yeah, in barren there is a lot of reduction. So this kind of change detection you can always do, and if you take it forward with the help of some other algorithms and land use land cover change modeling, then you can always predict the land use maps for the future, or you can project the future land uses. Like what we have to do, you need to have the variety of drivers of spatial changes. They go as an input into the land use change models. So in this particular case, we have used a ANN MLP based land use change modeling. So we have taken various input, like we have taken the elevation or the slope, percentage slope. We have taken the drainage or the distance from the drainage. So these are the various factors like biophysical factors, which are mainly the elevation, slope, channel distances, river distances. Socioeconomic factors, which includes the population density, literacy rate of that particular region, as well as infrastructural drivers of change, like what is the distance from to the road, what is the distance to the you can say railway network, what are the distances from the urban clusters, and so on. As well as there are some spatial trends maps which are based on the changes which has been occurred into last 15 years. So we have taken the 2000 and 2015 land uses as a in order to get the spatial trends of this particular region. And finally, we could able to achieve this projected land use maps of year 2030, 2060 and 2019 for this Yunan basin. So here you can see in the 2019, it has been projected with this particular inputs. This could be the changes in the changes into the Yunan basin. So there will be lot many urban clusters which may come up in the near future and the later future as well as. Agriculture drought assessment monitoring system, which is actually operational. If you go onto this particular link, then you can find out this NADMS, which actually which is based on the NDVI. As I have told you, this is one of the vegetation indices, which is again derived from NOAA AVHRR remote sensing data, and it is covering the pan-India, wherein this NDWI, the normalized difference wetness index, which is also being used for this particular developing this information. It is from the MODIS data, which is at the spatial resolution of 250 meters and so on. So what they have done, they have actually developed a soil moisture index, and based on that soil moisture index, they predict better whether there is a agriculture drought conditions exist in particular region or not. So you can just imagine or perceive what kind of information you can generate from the remote sensing data and the application of GIS. So this is another scheme wherein you can get the various kind of drought indicator and you can compare those drought indices. So you can always take the SMAP. SMAP is a satellite map, SMAP and SMOS. These are soil maps from the satellite data. And with the Palmer model is a drought model wherein you can make some data assimilation and generate some RZSM maps, and then you can find out some kind of anomalies whether they are persisting or not. Then you can see the variability of the soil moisture and the precipitation, and NDVI anomalies also you can get from the NOAA or from MODIS or Indian remote sensing satellite like LIS-3 and LIS-4. They can also be used in order to get this standardized precipitation indices for 3 months, 6 months and 9 months, and all those goes as an input in order to get the drought indices. And we are also, one of our MTech students, they have attempted on integrating the multi-criteria decision making, that is an MCDM and GIS technique for drought assessment. So what we have done, we have actually done this study for the Banda district of Uttar Pradesh. So we have produced variety of spatial maps for the district like rainfall map, temperature maps, humidity, slope maps, LULC maps, population maps, agricultural labor which are present in particular blocks, soil maps, groundwater yield maps with the help of the various observation wells, and after doing a particular you can say multi-criteria decision making, we have identified some kind of weightage to every particular individual parameters, and then we rank those, and finally we could get this drought severity map pixel wise in the complete district. So this kind of study can easily be done for any kind of basin or any administrative units also, so that you can have some focused area. That means in which areas the policymakers or the local bodies, they have to act immediately, and which can be reacted later on, or there are the moderate things are there. So yes, this was the thing. There is a pairwise comparison of the metrics for all the criteria. So obviously it's a kind of assignment, MCDM assignment, and finally we could get a weight for individual component, and finally we could get a ranking based on their weights, and those weights can be always do some kind of overlapping as well as crossing of the maps in order to produce the final drop severity maps. If you talk about the irrigation water management, so variety of application we can do for irrigation water management. So these are the few applications, like we can always do irrigation infrastructure mapping as well as irrigation potential assessment. That is called IP assessment, which is an essential part of any command area program, IP assessment. Apart from that, the crop acreage or as well as the crop water demand estimation, water logging and soil salinity assessment, conjunctive water use planning for the irrigation command, and finally, once we are doing all these activities for 3, 4 years or 10 years, then we can always do this performance evaluation of a irrigation project at the designated level, maybe for after 3 years, after 5 years, and so on. So all these applications, they need a variety of inputs, which mainly includes the topographical information. That means what is the elevation at different portions, the soil information, climatic parameters, and presence of the various irrigation infrastructures, cropping pattern, and so on. So, for example, if we talk about the different type of sensors which are available and their suitability for the irrigation water mapping. So if we see this list 4, it is all the sensors from Indian Remote Sensing Agency, and list 4 sensors. It actually a resolution of 5.8 meters. So it can be used for distinguishing between the minor canals having a width around 5 meters or more. So CAAST-1 data, which is a spatial resolution at 2.5 meters, it can be used for some minor canals having a width of around 2 meters or more. And the CAAST-2A and B data, which is a finest resolution what we have as of now, which is 1 meter, and it can be used for field channel having a width less than 1 meter. So here you can see the various satellite images of this list for CAAST-1 and 2. So CAAST-1 and 2, these are monochromatic sensors. They are having only one gray shade images, and this can be a we can also have a FCC for this in this. As I have told you that evapotranspiration has an important aspect which directly deals with that how much water is required for irrigation in particular region or in particular command, and that can be easily estimated with the help of remote sensing. So as of now, there are two popular models. One is C1 and second one is the metric models. Both are the surface energy balance model that can be used, and they basically works on the principle of estimating the residual energy. See, if you see over here, suppose we are receiving this Rn. Rn is nothing but the net radiation which is receiving, which a particular crop or vegetation received from the sun. Right? Few of the heat is being, so it's a simple energy balance equation. Et can be determined by Et is equal to Rn, the net radiation, the soil heat flux minus this one is sensible heat flux. Yeah. So we also have done this particular study. So what exactly they actually uses? So it is a condition that it must have a near infrared as well as thermal infrared bands in it. So this is important. That's why then only we can use this particular CAAST and metric models. So in our case, we have used around 20 satellite images with this path and row information. So path and rows are nothing but these are the identification of a particular region which are mandatory for identifying in case of remote sensing data. So we have this Landsat data which is at the rate of 30 meter spatial resolutions, and we have studied this from 2016 to 18, and we have used the Earth Explorer data. So as I've told you this, there are many intermediate products actually occurs or produces while we use this method. So we can have this land surface albedos, the NDVI maps, the land surface temperature maps, the net radiation maps, and finally with a defined algorithm we could get some instantaneous unit hydrogram. Instantaneous evapotranspirations. So this is the complete methodology. You can see the vegetation indices, NDVI and SAVI, LST, emissivity. These are all comes from the satellite images or Landsat data. Digital elevation map, again, it is a satellite product. And these actually produces the soil heat fluxes. And we also need to have some kind of validation from the ground, which comes from in the terms of meteorological data, wherein we can get sensible heat. So this sensible heat fluxes, soil heat fluxes, and with the selection of heat and cold pixel, this is an important, most important you can say aspect of CAAST and metrics. Selection of these pixels is very, very crucial as well as. So once we get all kind of component, then we have this net radiation, and then we go for the energy balance. And then for a particular pixel, that we can get instantaneous reference evapotranspiration fraction, and then the daily actual evapotranspiration can be calculated. So we also produces for the 20 images for the same area, we have produced this evapotranspiration. It's all into the unit is given here, the mm per day, right? So in that way, you can also have this spatial and temporal variation, right? It is from 2016 to 18. The temporal things are there, and especially in individual images, you can see which are the area having more evapotranspiration, which are the area having less amount of evapotranspirations. Soil erosion estimation as well as modeling. So as as agriculture people, we must be knowing this. India is a severely soil erosion affected country. One of the soil erosion affected country, around 187 million hectare out of our total 328 million hectares is subjected to those water erosion related problems. So actually this is actually resulting in heavy sedimentation of our reservoir and dams, which is actually reducing their life storage capacity and finally affecting the lifespan of those big infrastructures. And around 5,000 million tons of the soil is being washed up from the various areas annually due to runoff. So the soil erosion and information related to the soil erosion estimation is an important activity from agriculture as well as agriculture engineering as well as hydrological point of view. And there are many models are developed for this soil loss erosion and estimation, like USLE, that is universal soil loss equations, the modified equation, the revised equation, and other equations like the Morgan, Finlay, and so many equations are there. And if we take the USLE or MUSLE, the simple equation is like this: A is equal to RKLSCP. It is the simplest form of the equation wherein you can get the spatial average soil loss tons per hectare per year if you provide them the rainfall erodibility factor, the soil erodibility factor, that is K, L and S is the soil length and the soil steepness factor, and C is the soil cover factor or density factor. It varies, generally it varies from 0 to 1. And P is the crop management or practice factor. It is from 0 to 1. So once you got all these values, you can easily get the value of K. So how the remote sensing can help on these equations? If you have the spatial maps of each of this component, then you can always get the soil erosion. So what you have to do, so this is a simple methodology which can be applicable for calculating or estimating the annual soil loss with the help of remote sensing and GIS. So what do you need? You need an NDVI map. An NDVI map, again, you can get it from the Landsat images. Again, you need simple NIR band and the red band, you will get the NDVI map. And this NDVI map will lead to crop management maps because it will highlight all your vegetation, right? And second one is the land use land cover map, which can be again produced from image classification of maybe from the Sentinel-2 or land use land cover or the list 3 or list 4 data. The soil map is a spatial map. A lot of maps are available, maybe from the FAO has provided a global map. And apart from that, the NDSSLUP, which is a responsible agency for producing this kind of soil maps in India. So we can get the map from them, and we need to digitize those maps as the digitized version is not available. And rainfall data, obviously, it is available in terms of the rainfall series can be collected from IMD. IMD is again, DEM is again as a satellite product which can directly be used. So from the this is the time series data, the rainfall data. Once you got all the time series and you got average annual rainfalls values for a different, you can say points or different grids, you can also always have an interpolation and you can produce an annual rainfall map for a particular reason. And from the annual rainfall maps, you can get or you can produce this soil erodibility map with the help of equations which are given in the literature. And with the help of DEM, you can always get this flow accumulation maps and the soil maps in degrees. Okay, you can always convert that. and with the help of this DEM, you can find the combined L and S, the soil length and soil stiffness factor. So, and apart from that, from the land use maps, you can always get what kind of conservation practices you can apply or you can plan for the area so that you can produce a P factor map over here. And from land use also, you can get organic matter map. And finally, with the help of the crossing of the soil map and the land use map, you can get some soil erodibility maps. So all the factors are K, S, all LS, C, and P. All these factors are now we have generated in the form of WAC. And then once we got a, then we can make a cross of this maps and then we can get a annual soil loss. So it's a simple methodology. So which are highly useful, particularly for the areas which are not accessible, or it can be used for very first-hand assessment of soil losses for any reason. Yeah, if you see this slide, then you can easily correlate these. These are the images from a glacier region, and this is a very famous glacier of India called the Gangotri Glacier. So we can also do some kind of continuous monitoring for our snow and glacier resources. See, in 1976, this was the C, 50, 2010. These are the different period satellite images of the Gangotri glaciers. So here you can see this is the snout. So snout is a bit retreating. The next picture will make you more clear. So yeah. So this is the more clear, you can say, three-dimensional picture of or image of the Gangotri glacier. So here you can see in 1954 the dotted lines. This is the estimate where earlier the Gangotri glacier was, right? And this yellow one is 2003's assessment with the satellite images, and the green line here you can see this was done in 2010, and so on. So this kind of analysis, while doing this kind of analysis, we can always monitor what is the extent of the glacier, whether it is advancing, whether it is retreating or not. In the third report of IPCC, it was mentioned that the Gangotri glacier and most of the Indian glaciers, they will be vanished by 2035. But with our glacier studies, the threat was not that high, and now the IPCC has also taken back their statements that the Indian glaciers are not retreating that fast. Apart from that, there is a Karakoram anomaly has been identified. That means the glaciers of the Karakoram is advancing, and how we could understand or get that was possible only with the help of remote sensing and GIS. So just to show you how this snow resources or snow cover actually happens. So this is the image of January 2008. See, this is April 2008. This is August, so almost all the snow has been gone. September, again the snow is getting some momentum. Finally, December, some more snow is there. So in that way, you can monitor the snow with a time frame, different time frames. Apart from that, if you talk about the hydrological point of view, we need to monitor the different kind of water bodies in order to know what is the water available to us. So the remote sensing agency, images can also be used for identifying or allocating what is the water body location. So these are the actual remote sensing images. Here you can see, and these are their water body extractions with the help of the various tools. So if you know the depth and if you have developed some kind of model area depth versus the total volume, then always if you have the area of that water body, you can always calculate the total volume available in that particular dam or in that reservoir. So immediately you can get what is the water availability in particular reservoir, and with the availability of the water you can operate your dam you can say more efficiently. That means whether you have to release the water for agriculture or not, or how much water has to be released from a dam for drinking, for agriculture, and so on. So this is the same thing you can see. This is the scene of October 2018. The reservoir having full of water. In the April, starting of the summer, the reservoir get, the water of the spread get reduced, and by the peak summer, the spread of the water is very much declined. So accordingly, we can have the area, and finally we can get the volume, and we can change our dam operational policies based on the availability of the water. So these are the actual field application of the remote sensing. Apart from that, you can monitor the sea surface temperature as well as the land surface temperature. So in one of our MTech study, we have identified the urban heat islands effect in the Lucknow city. It has been understood that wherever there is a more of urban areas, the temperature of that particular region goes up, and the surrounding regions, or you can say the rural areas having a low air temperature. So we have done some kind of analysis, and we find this it's a kind of urban heat island effect, which is very much essential in order to study as we are moving ahead with the smart city concept for under the leadership of our Prime Minister. Apart from that, we can always monitor the soil moisture as well as produce some kind of soil moisture products. This is for SMAP, the soil moisture active passive sensors mission. It is from NASA, US. But yes, in India, the SEC Ahmedabad, the Space Application Center Ahmedabad, they are also actually calculating and deriving the soil wetness index for whole of the India on daily basis, and they are taking SMAP as their input, and with some processing, they are actually producing this kind of maps at 1 square kilometer for India. So again, this kind of soil saturation or wetness conditions, based on that, we can always assess whether what kind of irrigation is needed. Yeah, groundwater mapping also can be done with the help of GIS. Obviously, this requires the integration of variety of layers, and it includes mainly the groundwater mainly includes the geology, geomorphology, what kind of structural presence is there, whether there is a fractures or faults are there or not, what is the hydrological conditions, and what is the variety of base information also needed for creating this groundwater prospect maps. So Rajiv Gandhi National Drinking Water Mission project is in process at India level. So right now it will be cover all of the states, but in phase 1 and phase 2, few of the states has been covered. So what we need, again, we need these all layers. So see, different type of layers are there, and once you integrate all those layers, you can achieve this groundwater prospect maps. Rainwater harvesting is one of the, you can say, talk of the town all the nowadays. So, but for agricultural water management or waterside management activities, we also need to identify what is the suitable site for rainwater harvesting structures. So we can always do that with the help of remote sensing and GIS application. So this is a kind of model people generally used for identifying those sites. So what we need to do, we need to identify different criteria, like what is the land use over there, what is the runoff depth, what is the soil texture available there, what is the slope available in that particular region, and what are the different kind of streams available. And once all we set these criteria, we need to reclassify them criteria, and then we create say 5 number or 6 number of classes. Then we define some kind of you can say suitability labels, as well as we define or allocate some scores for each of the class under each of the criteria. And we all integrate those things, or you can say we perform this overlaying operation in GIS for the layers in order to get the most suitable site which actually meets all our criteria. So it's very, very simple. You need to have a more porous soil over there in order to recharge the water. You need to have a mild slope so that the water can be stored and the structure should be a minimum one. And we also need to focus on whether it's a first order, second order stream and so on. So in that way, with our given weights or scores, we simply cross what is the ideal site for this groundwater recharge. Apart from that, the river morphology, you must heard about this term. So river morphology includes many things like the linear aspects, aerial aspects, the relief aspects. So the stream order, stream number, the stream order nothing but it is a very first stream, right? Wherein you can say this is the very primary order of stream which actually starts the formation of the river. When one first order streams meets, it becomes second order streams, and when two second order streams meets, it becomes third order streams. So earlier days, people used to just measure the length of these streams with the help of thread on a topo sheet, right? So we need to put thread here and then here. So we need to measure what is the length of thread, and then again we measure all the length of first order stream. Then only we add those length, and then we could get the length of total first order streams. Then similarly length of total second order streams and so on. But with the help of GIS, you get all this information just with a click of a button. So just imagine that was so tedious earlier, now it will become very, very easy. So that you can always find the order, the stream numbers. If you have the total number of streams, earlier we used to just count 1, 2, 3, 4, 5, 6 manually over topo sheets. Now in the GIS, you simply take an expression or you simply run a query and you will get the total number of different stream orders. And with the help of those numbers, you can have this bifurcation ratio or stream length. And for different stream orders, you can also create water sets. You can always get the drainage density, circulation ratio, and so on. So all this exercise earlier, it has been done manually on the topo sheet with the help of a planimeter or a thread. Now it all can be done with the help of remote sensing and GIS. So it becomes very, very easy. So this is a basic exercise for any kind of hydrological studies when we start. And we also need to know what is the order of our stream. So this particular catchment is a Tabi catchment. We have done study in the JNK. So it's a 6th order catchment. So why this catchment ordering is important? Because the order of the stream actually can tell you what kind of water site management structure you can put on that particular stream. If it is a 6th order stream, then certainly you have to go for a big check dam. Then only you can conserve some kind of water, as the water flow may be very high over here. Or in first order streams, the water flow may be very less. So that you can always go for the natural based treatment, maybe stone Givian structure or loose stone dams and all. Yeah, I mentioned this coastline zone management and hazard mapping can also be done. The coast zone is a region wherein you can find the land, the ocean is always there, atmosphere and ocean. So all these three actually interact in particular zone that is called coastal zone. So in that way, coastal zones are very, very important, as these are the habitat of diverse biodiversity, and these are the landforms, sea, shore, as well as hotspot of the water quality problems of India also. So why it is important for India? Because India has a very long coastline. See, we have more than 7,500 kilometer long coastline. So we have not many coastal areas, and we have this kind of issues in all those coastlines. Correct? And apart from that, these coastal zones, they are highly vulnerable to natural hazards as well as like cyclones and storms and tsunamis. So we need to keep an eye on those areas wherein this coastal zones can be warned in advance. Apart from that, the water quality aspect, if you see, the seawater intrusion is a major problem in the coastal areas, wherein the seawater ingresses into the mainland groundwater tables, and that the saline water of the sea, which actually spoils the fresh water of the mainland groundwater. So we need to identify and map that also. So in that way also it is very much important. So I take my leave. Thank you very much. Any questions or any query on my presentations? I will be more than happy to answer you people. Thank you very much. Yes.
Well, thank you very much, Dr. Manishji. You have covered the many things. Actually, this particular talk completes all the aspects which we are going to cover in detail in the due course of this training program. I'm very thankful, and you have covered in a very nice manner.
Thank you.
In the very first lecture, you have really given the information very comprehensively for the students as well as the younger scientists. So, if there is no query for the students or from the other participants, we are very much thankful to you, sir.
Thank you. Thank you very much.
Sir, good afternoon, sir.
Good afternoon.
Myself, Gautam, sir. I'm a PhD scholar. I'm doing my PhD research in agriculture meteorology.
Okay.
So regarding with this measurement of evapotranspiration, actually you are using Landsat 8 image, right, sir?
Right.
And land surface temperature has been extracted for only sensible heat. We counted meteorological data that indicates that those captured image will have the surface temperature of the time of capturing. So, so that's why we are using sensible heat, or there is any other reason, sir? And another doubt, sir, in microwave remote sensing also we can measure soil moisture level. So we can include that in this model, or we can do it separate way.
See, you're talking about microwave remote sensing about the soil moisture, right?
Yeah, sir. That is one part. That is different part. For that, in case of Landsat 8, the land surface temperature is only particular for the time of the image has been taken.
Agree. Actually, we have validated that data. You are right. Whenever the satellite passes and it is capturing the details, and that particular time only the LST or land surface temperature is available. So what we have put in our automatic weather station over there with lot many sensors. It also includes the air temperature sensors near to the surface. So we have calibrated those values. We have taken 20 number of images, and for all those 20 number images, we have the value for that particular time also. So we calibrated our things or model based on the actual data from the field.
Okay, sir. So the evapotranspiration rate which calculated by this model is accurate now, sir. There is no issue with real time measurement and model measurement. There is any variation. I'm asking level of variation, how much it will be, or it is.
There are a lot of variations because obviously you got a sensor from a point, and that point at the max you can compare with a pixel.
Okay, sir.
But pixel is again too large, and your sensor is very small, right?
Oh yes, sir. Yes, sir.
Again, this is a limitation of the remote sensing things, always will be a remote limitations.
Yes.
But what you can do, you can improve this thing with the many sensors available into nearby regions with different, which are representing different, you can say land use types, or different, you can say elevation things, and different physiographical these things, features.
Okay, sir.
So when once you have more number of calibration points, then you will have more confidence in your model.
Okay. Okay. Thank you. Thank you.
That is again always a trade-off. How many sensors you have to put so in order to calibrate your models.
Yeah. Sir. Yeah. Okay.
Anybody?
Sir, there is a question in the chat box also.
How to delineate? So it actually question is about how we can delineate the artificial recharge zone from groundwater using AHP. AHP is a Arthis hierarchical processes. So it is a kind of multi-criteria methodology wherein we can have a multi-criteria for in order to identify for a recharge zone. So groundwater recharging, you need to know many of the features like what is the geology or hydrogeology of that particular region, whether there is a presence of fractures or faults or not, whether it's a salt or whether it's a sedimentary rock or whether it's a alluvial kind of things. So this is the first and foremost important aspect we need to take into account. Secondly, again, the basic things like what is the elevation, what is the availability of the flow which comes from the runoff depth, and lot many things are there. So yeah, I can give you some references on that. So Gautam, if you drop your email, I can send you something. Vinay Gautam. Okay. So my lecture actually just covers the what kind of applications we can do. Quality, yes, quality, not very much work has been done, but yes, the saline water, fresh water, this water can be easily distinguished with the help of few sensors. If you see in case of the coastal line, you can always get some shallow water which is near to the coast and some deep sea water which actually represented the uh, quality. Yeah, I understand that groundwater. I don't think the remote sensing sensors are capable enough to penetrate into the soil. Still, the soil moisture we can able to get the soil moisture information about say a few centimeters, say 1 or 2 centimeters. So groundwater out of question. So it doesn't go up to the groundwater levels. So as of now, best of my knowledge. Yeah, decadal groundwater data if you have, then you can have your model and remote sensing you cannot use, but the GIS part you can always use for the analysis if you have variety of layers with you. Okay, I will send you some relevant thing to you.
Okay, thank you, sir, for the informative session.
Thank you.
We hope that all the participants get benefited from your session.
I hope so.
Thank you very much.
Okay, thank you.